We have now seen an example in which we found the general solution to a linear system of differential equations of the form y prime equals a times y, where y is the vector function xy and a is the coefficient matrix a, b, c, d. Let's recap that process in the case where a has distinct eigenvalues lambda 1 and lambda 2. Remember, our general solution will depend on those eigenvalues and their eigenvectors, and we need them to be distinct so that we know the eigenvectors are linearly independent, and thus we have the general solution. To start, we find lambda 1 and lambda 2 as roots of the characteristic equation, which is given by 0 equals the determinant of our matrix A minus lambda I. That is, the determinant of A minus lambda, B, C, D minus lambda, where we subtract lambda from the diagonal. And when we compute this, we get lambda squared minus A plus D lambda plus A times D minus BC. So this gives us a quadratic equation, which we can solve either by factoring or using the quadratic formula. Once we find lambda 1 and lambda 2, then separately for each, we need to find their eigenvectors v1 and v2, satisfying the definition of an eigenvalue and eigenvector that a times v equals lambda times v. Remember, for lambda 1 and lambda 2 not equal to each other, the eigenvectors are going to be linearly independent, and thus the function y equals c1 e to the lambda 1t times v1 plus c2 e to the lambda 2t times v2 gives the general solution to our linear system. I want to point out a couple of notes here. By building up this theory, we have changed the process of solving a system of differential equations into a linear algebra process of finding eigenvalues and eigenvectors. If we can find those two things, then we can build our general solution. Also, the solutions y1 equals e to the lambda 1t times v1 and y2 equals e to the lambda 2t times v2 correspond to the straight line solutions that we saw in the phase plane. This observation, remember, is what led us to build the theory in the way we did.